66 million years ago, something hit the Earth. You know this story. An asteroid, the Yucatan Peninsula, a crater 200 kilometers wide, the end of the non-avian dinosaurs, and roughly 75% of all species on the planet. It's one of the most well-known events in the history of life on Earth, and we've been studying its aftermath for decades. But here's what we didn't know until last week. We didn't know what that asteroid actually was. Not really. We knew it hit. We knew approximately where it came from, somewhere beyond Jupiter, from the cold outer reaches of the solar system. We knew its size, roughly 15 to 25 kilometers across. We knew its speed, about 64,000 kilometers per hour when it entered the atmosphere. What we didn't know was its composition, and it turns out that matters enormously, not just for understanding what happened 66 million years ago, but for understanding how we've been telling the extinction story wrong. A study published July 17, 2026, in the journal Science Advances changed that, and the answer is genuinely strange. The asteroid that ended the age of dinosaurs was, with high probability, a CO chondrite, a type of space rock so rare that it makes up only a tiny fraction of all meteorites recovered on Earth.
To understand why that matters, you need to understand what a CO chondrite actually is, and why finding one responsible for the most consequential impact in the last 100 million years prompted one of the study's researchers to say simply, "Being struck by such a rare object highlights just how unlucky the dinosaurs were." CO chondrites are among the oldest and most primitive materials in the solar system. They formed in the very early days of the solar system's history, before the planets existed, in the cold outer regions, far beyond what would become Jupiter. They are carbon-rich, water-poor, and, crucially, extremely low in sulfur. They are not the kind of rock you find in museum collections. Carbonaceous chondrites, the broader family they belong to, make up only about 5% of all meteorites ever recovered on Earth. CO chondrites are a small fraction of that already small fraction. They are, by any measure, rare visitors to the inner solar system.
To figure out that the Chicxulub impactor was one of them, the research team had to get creative. The asteroid itself, of course, no longer exists. When a 15-kilometer rock hits the Earth at 64,000 kilometers per hour, the energy released is approximately 2 million times greater than the largest nuclear weapon ever detonated. The asteroid vaporized almost instantly on impact. What it left behind was a thin layer of material, clay essentially, that spread across the entire surface of the planet in the months following the impact. This thin layer, called the KPG boundary, can be found in rock formations all over the world, including in cliff faces in Denmark, road cuts in Spain, and hillsides in Italy. It sits in the geological record like a bookmark, a physical line between the world that existed before the impact and the world that came after it. The team, led by researchers from the University of British Columbia, Paris, Brussels, and Vienna, collected samples of this boundary clay from sites in Stevensklint in Denmark, Caravaca in Spain, and several locations in Italy. Then, they did something that wasn't technically feasible a decade ago. They measured the nickel isotope ratios in those samples with enough precision to distinguish between different types of space rock. Every type of asteroid has a slightly different isotopic fingerprint, a ratio of different forms of the same element that reflects where and when that rock formed in the early solar system. Nickel is particularly useful for this because it's abundant enough in the boundary clay to measure, and because different meteorite types have distinctly different nickel signatures.
The team compared their boundary clay measurements against the signatures of 11 different carbonaceous meteorite types and found the closest match, CO chondrites. This is where the story gets genuinely unexpected. For decades, the leading explanation for how the Chicxulub impact caused such a catastrophic extinction went roughly like this. The asteroid hit the sulfur-rich rocks of the Yucatan Peninsula, releasing enormous quantities of sulfur dioxide into the atmosphere. That sulfur formed aerosols, sulfate particles, that reflected sunlight back into space, cooling the planet dramatically and triggering what is sometimes called an impact winter.
Combined with the initial heat pulse, the fires, and the subsequent cold and dark, the sulfur aerosols were considered one of the primary kill mechanisms. The CO chondrite identification complicates this significantly. CO chondrites are extremely poor in sulfur. If the asteroid itself contributed very little sulfur to the event, then the sulfur that entered the atmosphere after the impact came primarily from the rocks it hit, the sulfate-rich evaporites of the Yucatan, rather than from the impactor itself. That changes the quantitative model substantially. The study's authors calculated that the impactor likely contributed only about half as much sulfur as previous studies estimated. So if sulfur from the asteroid was less important than everyone thought, what actually drove the mass extinction? The answer the study points toward is fine silicate dust. When a CO chondrite, dry, carbon-rich, low and volatile elements, vaporizes on impact, it releases enormous quantities of fine mineral dust into the upper atmosphere. Unlike sulfur aerosols, which settle out of the atmosphere within a few years, fine silicate dust can remain suspended in the stratosphere for much longer, blocking sunlight more persistently. The darkness that killed the dinosaurs by shutting down photosynthesis, collapsing food chains, and cooling the planet may have been caused more by a sustained dust veil than by the sulfur winter that most textbooks describe. This is not a small revision. It changes the physical mechanism of the extinction. It changes the timeline of the darkening. It changes the severity models for what a similar impact would do today. And it tells us something specific about where the asteroid came from. The CO chondrite origin points toward the outer asteroid belts near Jupiter, or possibly to even more distant parts of the early solar system. There's a detail in this story that is easy to overlook, but that gives it a specific weight. The researchers note that CO chondrites are not just rare in museums, they are rare in the solar system. The chance of the Earth being struck by one rather than by one of the far more common types of asteroids was genuinely unlikely. This is not a comforting thought dressed up as science. It's a statistical reality about what happened to the dinosaurs. They were killed by one of the rarest types of objects the solar system could have sent their way. Philippe Claes, a geochemist at Vrije University Brussels who worked on the study, put it plainly. Being struck by such a rare, distant projectile really underscores how unlucky the dinosaurs were. What the study doesn't resolve, and couldn't, is the exact origin location of this specific rock. The leading hypothesis is the outer regions of the main asteroid belt, beyond what is called the 3-to-1 resonance with Jupiter, a gravitational sweet spot where orbital mechanics can destabilize rocks and fling them inward toward the inner solar system over millions of years. The study doesn't rule out an origin even further out, in the trans-Neptunian region. Those questions remain open, and the researchers believe that combining nickel isotope measurements with chromium and ruthenium data in future work may eventually narrow the origin further. For now, what we know is this. On a day 66 million years ago, one of the rarest types of rocks in the solar system crossed billions of kilometers of space, entered Earth's atmosphere at 40 times the speed of a rifle bullet, and ended the reign of the non-avian dinosaurs. The dust it threw into the sky did more of the killing than the sulfur, and the darkness lasted longer and cut deeper than previous models assumed. We've been asking what killed the dinosaurs for as long as we've known dinosaurs existed. We've known for decades that it was an asteroid. We've known for years approximately where that asteroid came from. Now we know what it was made of, and that knowledge has, in the most precise and unexpected way, changed the answer to the question we thought we'd already answered. If stories like this, where science takes a question we thought was closed and reopens it with new precision, are what you want more of, stick around. And let me know in the comments, does knowing the extinction was caused by one of the rarest types of asteroids in the solar system change how you think about the event? And knowing what we know now about the dust mechanism, does the extinction story feel more or less survivable than you assumed?